let's dive right in and suppose that we were not computer experts, but we were some non-computer experts and wanted to use some of these fancy new cryptocurrencies, just like Bitcoin, everyone nowadays is talking about. So, how can we start? Probably we just look it up on the internet, and at some point we might find an account on this web page. It's the web page from Bitcoin, and it looks good. I can download Bitcoin, right? If I want to use Bitcoin, I probably have to download it. Unfortunately, when you understand this text here, so if you understand it at all, then you realize that you're probably on the wrong track, because it says, oh, you have to download 200 gigabytes of data, and probably it will fill up your whole disk space, and that might actually not be what you want to do while using Bitcoin. And yeah, the problem here is Bitcoin grows fast. It's not really a problem of Bitcoin. All of the cryptocurrencies basically have this problem that blockchains are growing. So you might just ask some of your friends, so how can I actually really use Bitcoin? I don't want to download 200 gigabytes to use it. And they might point you to one of these clients, for example. This is an SPV client, simple payment verification, like Electrum, and it's still not really usable, so you're not really user-friendly. At least if you're not a computer expert and you don't know anything about cryptocurrencies yet, then this might be quite hard to use. Plus, there were some phishing attempts in this particular client, for example, so it's not the ideal solution, probably. So what most non-computer experts will probably end up with is using something like Coinbase. That's pretty nice because it's something people recognize. It's like a web page, like online banking, so it's what is usable for the everyday person, basically. But somehow it, of course, defeats the purpose of cryptocurrencies, because it's a centralized service, you don't own your own private key, and that's the bad part of it. But so why do people actually choose Coinbase? And to understand that, you have to look at what do people expect from a virtual or also a real currency, and what do they know. So what do they already know? They are used to traditional banks, they work in the offline setting. Credit cards, they are somehow online, but usually most of the stuff works offline. You go to the shop and you use a credit card. But they also know online banking, and this is something web-based, so very much like Coinbase, and PayPal as well, it's web-based. And I think that's one of the reasons why people like Coinbase so much. But can't we just build a cryptocurrency, or can we build a better Coinbase, basically, that doesn't have the disadvantage of Coinbase? And that's where we started, basically, and we took a look at basically the ideal solution. And we thought, okay, it should be something which is web-based, so that people know that and know how to use it. But it should be in a way that the keys are not stored on a central server, but at people's computers, basically. So it's should be non-custodial. We still want it to be fast and lightweight as Coinbase, so we don't have to download 200 gigabytes of data in our browser, basically, and it should also work on mobile devices. Ideally, we also don't want any trusted middleman in there, and at least the statements that we get should be provable, basically. And of course, since we strive for usability, it should be easy to use, and not only by users, but also by developers, basically. And that is what we try to do with Nimiq, and this is the first part of my talk. And I'll not only show you what we built, but also how we basically, the whole story from the beginning, where we failed, what we learned from there, and how we improved. And in the second part of my talk, I'll quickly talk about two other points on our roadmap. One is exchanging fiat and cryptocurrencies without additional trust requirements, and the second one is our new consensus protocol that we've worked on. Okay, let's start with the first part and go back to this ideal solution. So what kind of implications do these points actually have? We want a web-based solution, so probably the main development language we have to use is JavaScript. And since there is no other cryptocurrency that's written in JavaScript, it requires a complete implementation from scratch. Then, okay, secure storage of keys, we can achieve that somehow. And fast and lightweight, no trusted middleman. For that, we need some form of light client or also simple payment verification. And in our very first version, we thought that something called the mini blockchain scheme might be perfect for that. So that's what we tried to use first, and I'll talk about that in a minute. And we hope that basically easy to use and integrate, that just follows from being web-based. But we'll see in a moment. Okay, so what we actually wanted to do here is we implement a blockchain that runs in your browser. And since this is already quite a lot of work to do, we wanted to keep everything else simple. So we rely on proof of work and well-tested protocols, basically. We took parts from Bitcoin and Ethereum, but we removed the difficult parts like the scripting language and focused on pure payments. And there was one paper from Arthur Gervais, who also gave a talk a few days earlier here. And from there we basically took the idea of reducing the block time to 1 minute. Okay, so but having a web-based currency, what other kind of issues can we foresee? We need two different types of clients somehow, because we don't only want to have clients that run in the browser, we also want to have servers that run our currency. But we don't want to implement two complete new clients. So what we decided for is that we actually share the code base between the browser clients and the server clients, at least large parts of this code base. And for that, because we wanted to use JavaScript, the servers, they have to run Node.js. That's the logical conclusion of that, basically. The next problem with being web-based is, okay, somehow these backbone server clients, they have to communicate with the browsers. How do you do that? And fortunately, web technologies, there are some available that facilitate that. So we decided that the servers, they communicate via WebSocket. That's a protocol built on top of TCP. And why didn't we use just TCP like Bitcoin? Because the browsers, they can't talk TCP, but they understand WebSockets. And we'll see in a moment why this is important. But okay, how can the browsers communicate? Okay, browser-to-browser communication does not work with WebSockets, but there's something called WebRTC, and that allows browser-to-browser communication. And now we can use WebSockets to also connect the browsers to these servers, because WebSocket basically always works from the browser to some other node which has a host name or an IP address, and so this way it works. So somehow we solved this communication problem using WebSockets and WebRTC, and we have one huge network that combines the servers and the browsers. Okay, exactly, they're in the same network, and that also means that we don't need any other nodes that basically serve the data for the browser clients, but the browser clients are part of the blockchain network where also all the other, let's say, real clients are in. They mostly run the same code, so we don't have to basically implement two types of clients, completely new types of clients. And yes, browsers support JavaScript by default, backbone nodes, they run the whole thing using Node.js. And theoretically, you could even mine in the browser, and we had that as a toy example in the beginning, but of course it doesn't make sense from an economic point of view, because your browser is just too slow. Okay, so these were two of the issues that we encountered, and the third one is, how do we manage the cryptography in the browser? There is something called Web Crypto API, and this is a cryptographic API exactly for browsers. It's implemented by the browser, and so we thought, oh, that might be actually quite good because it should be fast enough, but it's also very limited. So it only supports one hash function, which is SHA, so we had to use that for the proof of work. And signatures, it supports ECDSA, but only with NIST curves, and so we had to use that for now as well. It's not really ideal, but that's what we started with, basically. Okay, and that's how this whole idea of this blockchain in the browser started. Some of the stuff here we've already seen, and I want to talk about two points here that I have not talked about until now, which is this mini blockchain scheme. We want to be fast and lightweight, so that it runs in your browser and also on mobile devices, and we want statements to be provable, basically. And for that we have two types of clients. The server nodes, they all run basically normal full nodes as you expected from Bitcoin, whereas the browser nodes, they run light clients. This is some lighter version basically using this mini blockchain scheme. And what does this mini blockchain scheme actually do? I'll tell you right now. So let's have a look at some normal blocks like they would occur in Bitcoin, for example. We have the header. This is the upper part here, which has a hash, a nonce, and a previous hash. And we have the body of the blocks, which contains the transactions. And so we have this chain of blocks, and this is basically how it looks like in Bitcoin. In Ethereum and also in the mini blockchain scheme, you have an additional field basically in this header. It's the accounts root. It's basically a commitment, a hash, to the list of balances in the system. And here I brought you an example. It's usually organized in a Merkle-Patricia tree, which is similar to how it works in Ethereum. And let's suppose we first have one address, which just contains zeros basically, and then in this account we have the balance for this address, and we have a nonce, and the nonce is required for replay protection. We'll see that in a moment too. But let's just add some more addresses basically. So in this tree, the shared prefixes always build a node in the tree. So we have two addresses that both start with 00, so we have one node that basically corresponds to this prefix 00, and the two accounts are below this node because they share the same prefix. If you now add another account that has a different prefix, we basically have at the top the root node which has the empty prefix. On the left hand side we have then the node that has the 00 prefix with the two accounts, and on the right hand side we have this single account that has the other prefix. Okay, as you can see here, we have different nonces in the accounts, and they are, as I said, required for replay protection. Basically, you just increment this nonce so that the nonce is part of the transaction, and you can't just take a signed transaction and replay it, because after the transaction has been executed once, the nonce changed in the account, and the same transaction is not valid anymore. But that also brings a huge problem in these kinds of accounts trees, basically, because even if the balance, like in the second account here, goes back to 0, you cannot delete the node from your tree. Because if you would delete this node from the tree, you would lose the information about the nonce, and if you reuse the account and send some new money onto that account, all of the previous transactions are replayable. So the problem with these kind of trees is that they grow indefinitely and you cannot easily prune the accounts. That's also a problem that Ethereum has right now. Okay, so let's go back to the blocks, and basically you hash this tree, and the top hash is the one that is now part of these blocks. The mini blockchain scheme now improves the synchronization in terms of just leaving out all of the transactions. So you only synchronize the header chain, which should be much shorter, and at the very end, you synchronize this tree. So you know all the account balances, and you know that basically the hash of that corresponds to the hash in the last block, and that should be correct because you synchronized the whole header chain. And that was our very first implementation. And that one we launched then in 2017. as the Nimiq beta network, and I'll tell you about the lessons that we learned from that. First of all, the synchronization took way too long. So it didn't really work out as intended, and our temporary solution was to introduce checkpoints so that you don't have to synchronize the whole header chain basically, but you just start at some point later on and synchronize parts of the header chain. Of course, that improves synchronization time, but it doesn't really scale and it's not an ideal solution. The second thing is some functionality was just too slow in the browser. Especially the Web Crypto API, which was actually designed to do cryptography in the browser, it was too slow. And that meant that verification of signatures and hashes, two essential functions in blockchains, they were too slow. So what did we do to basically counter these problems? For the synchronization issue, we switched to non-interactive proofs of proof of work. And I'll show you how that works in a second. You also heard of that before, during the last days. And regarding the being just too slow, there we used C code, because nowadays you can just compile Z code to WebAssembly, and then WebAssembly runs in the browser, and that's even faster. And that also allowed us to switch to better algorithms, so we switched to Schnorr signatures, ED25519, and we switched to Argon 2 as a hash algorithm instead of SHA. Oh, and another thing for usability, basically what we did is we introduced addresses in the IBAN format that is quite used here in the EU, and so basically it's something people can recognize because it just looks just like your normal bank account number here. Okay, let's talk about the non-interactive proofs of proof of work. The very basic idea here is that some blocks, by chance, when mining them, they have a significantly harder proof of work than what is actually required to make this block being accepted. But if you want to reproduce this significantly harder proof of work, because you're an attacker, that's hard if you want to do that on purpose. And if you even have a chain of these very hard blocks that you got by chance while mining, reproducing such a chain on purpose is very hard for an attacker to build. So let's suppose this is basically our blockchain, the different blocks, and now we have basically each of these slots is one block, and on the y-axis basically we have the hardness. So those blocks that have that are 4 points high here, these are the hardest blocks, and now each of the blocks basically points back to other hard blocks. Exactly, this for example block number 3 is one block that was just hard by chance. And so let's briefly recap this proof of work thing to show you what it actually means mathematically to be hard by chance. So in proof of work, the goal is basically to increment this nonce and find a block so that the hash of the block is less than the target value. And now, for example, the target could be 2 to the 240 in this case. And if our block was symbolically here the string hello world and 0 is the nonce, we just increment that, and at some point we get a nonce for which the hash of it is lower than the target value. And it might be that by chance this hash value is much lower than the target value, and that's a hard block by chance basically. That's what I mean with that. Okay, and if you have then such a chain in the non-interactive proofs of proof of work setting, basically these hard blocks allow us to skip a lot of the other blocks during the synchronization. So very roughly speaking, we just have to sync logarithmic number of blocks. Actually, the proof construction is a bit more involved because you have to compare basically 2 different types of potentially 2 different of these hard chains, but this is basically the intuitive version of it. And so instead of syncing the whole chain, you just would need to sync basically the block on the left-hand side, then the one with the 3 up there, one with the 2, and the 0, 1. So that's the part that you could synchronize. Okay, and so we implemented that, and we had the first update of our beta network or test network that we called Luna, and it was just like 5 months after releasing the first version, basically, and that already worked quite well. But we still had some things to fix, basically. For example, remember that I said in this accounts tree setting, the bad part is that you can't prune blocks with empty balances, and the tree just keeps growing and growing. So we just removed the accounts nonce from the tree, and that allows us to also prune basically empty accounts. But we still need some kind of replay protection. So instead of having the nonce here, we removed it, and we introduced something called validity start height. So basically the transaction has to specify the time frame in which it is valid, and no transaction with the same appearance can be included in the blockchain in this time frame. So what that means is that transactions are actually only valid for 2 hours, so if they are not mined within 2 hours or something like this, they are invalid and you have to do a new transaction. Exactly. But it allows us, on the other hand, to prune these empty accounts from the account stream. So it's a trade-off. We have this transaction validity window of 2 hours, basically, but in our case, it's not like it takes that long for transactions to be mined. Okay, so what else did we add? We have 2 different types of contracts. We have HDLCs, you have seen them before as well, and I'll introduce them later on in my talk as well. And HDLCs, why did we add them to our blockchain? Because we want to have interoperability and potentially layer 2 solutions. That's why we have that. We also have vesting contracts, so we have a foundation and Nimiq, and that owns some Nimiq, of course, and they are released over time, and that's why we have a vesting contract. So these contracts are hard-coded. That means we don't have a contract language. Nobody can just create new contracts. You can deploy these types of contracts, but the code of the contracts is written in JavaScript and hard-coded in the consensus rules, basically. And that's how we also released our main network then in 2018. So it ran now for basically a bit more than a year, and it went quite well. So let's have a look at what of these points from this ideal solution that we wanted to implement we actually did. So we have a web-based solution. We also we also have a fast and lightweight synchronization. We don't need a trusted middleman here, even in the browser. And the other 2 points that are still open, I'll talk about now. So how are the private keys actually stored when you use it in the browser? So we have one origin called keygut.nimiq.com, and that's the one that stores your private keys. It's stored in something like some web storage API, so it's inside your browser basically. And then we have the online banking-like interface called safe.nimiq.com, and there you see your accounts and so on. And now if you want to sign a transaction, then there's some intermediary called hub.nimiq.com, and you basically, the online banking app says, please, I want to sign the transaction. So it functions very similar to a hardware wallet actually. And this one will forward it to the key guard, and that's the only one that knows this private key, and there you can, it's actually also encrypted, so you have to enter a password, and then the signed transaction is given back to the online banking interface. So the key never leaves this keyguard.nimiq.com. And that means that private keys that are stored there are guarded by something called the same origin policy, and that's a mechanism of the browsers that basically only allows scripts that have the same origin to allow the data of that origin. So only scripts that run under HTTPS and kiga.nimiq.com and on this port can actually access the private keys. So we took great care that everything that runs on kiga.nimiq.com, it's on a separate server, it's minimal scripting and security vetted, so that hopefully nobody can ever run another script on this domain, basically. Okay, that's how we implemented the secure storage of the keys. And so what about easy to use and integrate? Let me talk a bit about that. Okay, and let's go back to the current state of the art again. So, suppose we now got a Bitcoin client running. For example, we used Electrum, or even Coinbase, doesn't really matter for that purpose. And finally, we also have some Bitcoin to spend. We got them from an exchange, and now we go to some store, maybe an internet, and it says, oh, Bitcoin accepted here. How can we spend them? So we basically shop in this online shop, and afterwards we will be redirected to some web page like this, which says, okay, now please send, how much is it here? 0.0003 Bitcoin to this address. You can also scan this QR code, and that's how it's implemented right now. And the question is that really user-friendly? I would argue it's not user-friendly. Let's have a look at what people expect again. So, if I go online shopping, let's say on, maybe not Amazon, because there my credit card is already stored, but I go to some other online shop I've never visited before, then what I usually look for is, do they accept PayPal? Because that's a very easy option. I don't have to give them my credit card information, and I still can pay very easily. So, how does PayPal work? So, let's suppose we are in this shop. Here, this is from the PayPal demo web page, actually, and I want to buy this beautiful camera. So I just proceed to the checkout, or I say I want to pay with PayPal. Then the web page turns basically a bit black, and this PayPal window opens, and I can just enter my credentials. I can again see how much I want to pay, and I just say, okay, yeah, I want to pay that. And done. And the question is, now that we have this blockchain that runs in your browser, can you actually build something very similar to that? And it turns out, yes, we can. And I'll quickly show you this video that I just made a few days ago in our test network shop, basically, so that you can see how it works. Okay. Yeah. Okay, so here we went through the shopping experience basically, and now we want to pay. We just select the account we want to pay. We have to enter the password for decrypting the private key. And now you see it's syncing the consensus. And it already synchronized the consensus, and it's sending out the transaction now. The payment is successful, and the shop says, okay, everything's complete. Now at this point, the transaction is probably not in mind on the blockchain, but at least basically the order, that the payment is initiated, the transaction is sent out to the miners, and they can integrate it into the blockchain. And that's basically the experience that we wanted to build, because we wanted to have a very usable way to also spend your crypto and to interact with it in this online banking-like setting, basically. Okay, so I would argue that we also somehow succeeded, at least in this mission, building this paper-like checkout process and making it easy to use. But here I wrote, okay, it should be easy to use and integrate for users and devs. Actually, I only showed you the part for the users. How can users work with this, with Nimiq, basically? But what about the devs? After the break, you will have a hackathon, also sponsored by Nimiq basically, and there we will show you exactly how easy it is to integrate. And what you can do basically when you have a blockchain in the browser, because you can open an empty web page and you can interact with the blockchain just in your console basically, or you can write a very easy web page to do that. But okay, let's return to this talk. So, what have we seen so far? We wanted to build something in JavaScript. Yes, we did that. We still have proof of work, and it uses Argon 2, which we implemented by WebAssembly because that was faster. We have a protocol that resembles Bitcoin and Ethereum, so we took actually most parts of Bitcoin. From Ethereum, we took basically this accounts-based model instead of UTXO. And we have the 1 minute block time. We have the communication via WebSockets and WebRTC, so we have this huge network that includes both browsers and also the servers. But we completely scrapped the mini blockchain scheme because we then used proofs of proof of work, so Nimiq, and we also implemented accounts tree pruning via this transaction validity window. Okay, so let's summarize the first part. Basically, Nimiq 1.0, how I call it, we implement this well-running blockchain with a focus on simplicity and usability, and we tried to make the account handling very online banking-like, so that you have basically an experience very similar to what you already know, and also which is the reason why people actually choose Coinbase when they want to use Bitcoin. And we also have this integrated checkout flow, we have some plugins for that, and actually we will also support other cryptocurrencies soon, so we're not only focusing on Nimiq and Nimiq everywhere, but in the end you could use this same plugin to pay in other cryptocurrencies. Maybe it's not that useful then because these are not browser-based currencies, but at least you have a unified checkout flow basically. And we're still the first, or we were the first blockchain that is able to fully run in the browser, and up to now it's still possible to actually even run a full node in your browser. So I've tried that just a few weeks ago, and you don't have to use this light client in your browser, you can also run a full node in your browser, but I wouldn't recommend it for normal everyday use because it just takes very long. But it works. Okay, so more lessons learned. We actually noticed that setting up these server nodes is a real hassle, and that is because HTTPS sites may only use secure WebSockets, and secure WebSockets means, so basically the online banking solution wants to connect to a server node. The online banking solution is running on HTTPS, so it has to connect to a secure WebSocket node. And that means that all the server nodes, they require SSL TLS certificates, host names, and that's a hassle for a lot of people. So we also introduced additional support for insecure WebSocket, which only supports basically server-to-server communication then. Another thing is Node.js is also not the fastest implementation, so we also decided to implement the server version in a different language, and we chose Rust. Why did we choose Rust? Because it's memory safe, it's strongly typed, it has very good performance, it doesn't have a garbage collector, and it's also compilable to WebAssembly. So the end goal would actually be that we don't have to use JavaScript in the browser. We can implement everything in Rust. We can compile the Rust code to WebAssembly and ship this WebAssembly binary in the browser. And we actually completed the Rust implementation in March this year. It is not yet compilable to WebAssembly, but you can already run a server basically on that. Okay, so let's see. That was the first part of my talk basically, where we analyzed basically, or where I showed you the way from this idea of building the browser-based blockchain to where we are now, and also the problems that we encountered and how we fix them. And in this second part, I'd like to talk about something called OASIS. And for that, I first want to talk about HTLCs again. You've heard that before in this summer school already. It means hash time lock contract, or there are also other spellings. Basically, some people say it's hashed time locked contract, so with an ED at the end or not. You can argue about that, but it doesn't really matter for what they do. And so let's suppose we have two parties, Alice and Bob, and they want to exchange cryptocurrencies. And there's Alice, and Alice doesn't trust Bob at all, as you can see here. And so Alice has some Bitcoin, and Alice wants to send the Bitcoin to Bob, and Bob has some Ethereum and wants to send the Ethereum to Alice in exchange. But so usually, or normally, I could say, okay, one person has to go first, the other person has to go second. But nobody here wants to go first because they don't trust each other. Yeah. So what you can do is you can use HTLCs to do something which is also called atomic swap. And so Alice starts, and Alice creates a secret. So here the secret is very simple, it's called secret. And then Alice goes on and hashes the secret. So she has the secret value and the hash of the secret value. And then she creates on the Bitcoin blockchain this HTLC, and that means basically she creates a contract there that says, okay, release this Bitcoin to Bob if Bob, or if someone gives me some value X, which hashes to the hash of the secret. So it should basically mean if someone gives me the secret, give them Bitcoin to Bob. But it might also be that Bob will never basically claim this Bitcoin, and in that case, after a certain time has passed, the Bitcoin should go back to Alice. And now Bob, on the other hand, does the very same thing just on the Ethereum blockchain. But Bob doesn't know the secret. Bob only knows the hash of the secret, and he also creates a HTLC which says basically release this Ethereum to Alice if you get the secret, and release it to me after a timeout. So now only Alice knows the secret value, but Alice can now go to the Ethereum blockchain, post the secret value to the Ethereum blockchain, and that will release the funds, and the Ethereum will go over to Alice. But now, since everything is public on this blockchain, Bob on the other side, he can also look into the blockchain and extract basically the secret value and use it to claim his Bitcoin on the Bitcoin blockchain. And that's what is called an atomic swap using HTLCs. Okay, so why do you want to do that? It's for exchanging cryptocurrencies, for example, without trusting the counterparty, as we have seen. And as a textual description would be, Alice sets up this HTLC number 1 on one chain, which locks up the Bitcoin to Bob using this hash. Bob does the same, and both basically verify the contract on the other chain. And when Alice then captures the Ethereum from the second hash timer contract, using the secret becomes publicly known, and Bob can use the secret to capture the Bitcoin from the other hash timer contract. Okay, and that of course only works for cryptocurrencies that have this HTLC support. So if I have another cryptocurrency that doesn't have HTLC support, I can't do an atomic swap with that cryptocurrency. And so what is this OASIS? When we thought about that, we looked at basically that atomic swaps, they can do exactly this between different cryptocurrencies, but when you now look at normal fiat money like euro or dollar, there's a problem. You can't do that. Why? Because fiat dollar euros, they don't support HDLCs. So, exactly, and that's where we had the idea of building this open asset swap interaction scheme. That's how OASIS, that's what OASIS is, basically. And on an intuitive level, it's simply that we have a bank that simulates a blockchain, basically. This bank is, you have to trust the bank anyway, because if you own some euros or dollars and have them in the bank, you have to trust the bank. Yeah? And in this case, now the bank can basically just simulate being a blockchain, offer this HDLC support, and then you can interact with your bank like it was a blockchain. So I'll give you an example. We have here in the green box the fiat seller, which for example could be Alice, and in the red box we have the fiat buyer, and in the red box the fiat seller, which could be Bob, and both have bank accounts. And so the fiat buyer has some Bitcoin, for example, or some other cryptocurrency on the blockchain and wants to sell these to the red person here and wants to receive some fiat, of course. So, and for just for simplicity, let's just assume that the fiat seller is customer by a bank that supports this OASIS scheme, basically, but it's not necessarily like that, just for this example. And the other, the fiat buyer, he's a customer at any bank somewhere. And there's a link between the two banks. You can basically wire transfer funds using SEPA or SWIFT. Okay, what kind of interactions will we have in this scheme? Both the fiat buyer and the fiat seller, they, for example, they have to interact with the OASIS bank, so the one that supports the scheme, and they also have to interact with the blockchain. And let's suppose that they use, so both buyer and seller, they use a decentralized exchange, for example, so the decentralized exchange matches this order, and the rest is done between the other parties, as shown here. Okay, so let's see. I'll go through this example now step by step to show you how that could work and how basically you could, having a bank that supports this OASIS scheme, how you could have an atomic swap between fiat currencies and cryptocurrencies. So we have the fiat buyer. The fiat buyer creates, just like in the example before, some secret value. Here the secret value is shown by, or pictured by this key. And using this key, the fiat buyer creates a HDLC, so a hash table contract on the blockchain. And as you can see, it's addressed to the seller and it has some amount, here Nimiq, and a timeout, so the same as before. Now the fiat buyer has to tell the fiat seller, here's the contract. It can just basically give out the address of the contract, and the fiat seller then has to look at the blockchain, verify that this contract is there, and have a look at the contract, basically. Okay, and in the next step, the fiat seller goes to his bank and says, using this OASIS API, basically, I want to set up an HDLC, but just with my Europe account. And that's a service that the bank has to provide, basically, and it's some kind of authorization, how it's called here. It basically has exactly the same information as an HDLC. And it gets back, so the fiat seller gets back some kind of authorization token from the bank, which it gives to the fiat buyer, so that the fiat buyer can check that the bank also has this HDLC, so that this HDLC basically on the bank side really exists. And here is where the trust comes in, because of course the buyer has to trust the bank. If the bank says, here's basically the information for the HDLC, the buyer has to trust the bank that it actually complies with the contract there. Okay. Now the fiat buyer can use the secret value that it generated and the authorization token to initiate the transfer on the bank side to his own bank account. So this is the first part. But now, how does the fiat seller can complete this exchange on the blockchain side? The fiat seller has to go to the bank, to his bank, for example, and ask basically for this secret, because the secret has been provided to the bank before by the buyer. So now the seller also has the secret and can claim the funds on the blockchain. So let's talk about the trust model here. We have the blockchain, and the blockchain, there everyone just has to verify the contract of the opposite party basically on their own, and you have the distributed trust in the blockchain basically. On the bank side, you also need to verify that on the bank side the HUC is set up correctly, but you need to trust the bank that it complies with this contract. And as I said before, the people, they must trust their bank anyway, if they have euro or dollars at least. And plus there are some legal challenges to counter misbehavior. And we actually also implemented, or are about to implement this, using a German bank called the WEG Bank. So they will be the first one that provide this OASIS API. And another nice thing is that you actually don't need to be a customer there. They can basically just function as an escrow service. So the bank provides this contract. So from your bank you can send the funds there to create the contract, and the funds will leave the bank to the buyer's bank afterwards. Okay, so we have seen that we can actually build atomic swaps to fiat currencies using a trust model that already exists, because at least when we assume that we have to trust the bank anyway, and then we don't add additional trust relations in here. So it's something like we made the fiat currencies like euro and dollar blockchain compatible in this case here. I also have to say that using these HUCs, this is one use case, but other protocols are possible too. So it's not just basically limited to HUCs and atomic swaps in this case, but you could have any protocol, and the bank just provides some kind of API, and that also fits very nicely with some new regulation that just came into place here in Europe. I think it was starting September 1st, or maybe mid of September. The so-called PSD2 regulation, which basically tells banks that they have to have some programmable APIs, so it's a requirement, and some form of this blockchain compatible API is very nice for basically bridging the gap between fiat currencies and cryptocurrencies. And as I said, bank account with a support to bank is not a requirement, it also works without. And this particular OASIS scheme basically can be used for decentralized exchanges, OTC trading, or whatever you like to implement with it. Okay, so that was the second part, basically, and now I'm going to part 3 of the talk, which is the consensus protocol that we've come up with. Okay, so maybe you remember from the first part of the talk that Nimiq currently is a proof-of-work blockchain, and I particularly don't really like proof-of-work. Why don't I like proof-of-work? Because it's, for example, very bad for our environment. For example, in 2016, 70% of the Bitcoin hash rate came from China, and they use mainly coal to generate the electricity that is then used for Bitcoin mining. So it basically looks like in the picture up there. And also 1 year later, there was an estimate that Bitcoin already consumed as much energy as Denmark. So these estimates, as it says, these are estimates. You can't really verify whether it's really that much, but I can actually believe that in 2017 it was as much as Denmark, and now it's probably even more. But it doesn't have to be like that, because proof-of-stake protocols, they don't consume that much energy. They are, And that basically triggered our research into proof-of-stake protocols, and I'll now present you the outcome of our research there, which is the Albatross protocol. So I have two more reasons basically why we looked into proof-of-stake protocols, and they concern two other problems of proof-of-work protocols. One is the poor scalability, so proof-of-work protocols are generally slow, and the second one is they only offer probabilistic finality. And why is that a problem? You can see that here in the street. I hope it's large enough, the text. So it was maybe now a few months ago, but there was this hack at Binance, and people suggested that Binance could just rewrite the history of the Bitcoin blockchain. And that just works with proof of work, because if you could bribe the miners to basically just start at a previous block and revert the history. And this comes from the probabilistic finality. So overall, I have to say that actually a lot of consensus protocols already exist. There are also proof-of-stake consensus protocols. We've seen some other consensus protocols during the last days here at the summer school, and they each have different trade-offs. There are also other solutions to some of these problems. For example, the poor scalability can also be tackled by using layer 2 solutions like Lightning Network or Liquidity Network. We have seen a lot about off-chain protocols during the last days too. So these are other ways to tackle this problem. But nevertheless, we had some promising idea which we wanted to follow up, which is building an optimistic protocol. And I'll tell you in a second what an optimistic protocol means. And for this nice optimistic protocol, we came up with the name Albatross. So during the last days, you've probably heard PBFT already too. And PBFT is a means practical Byzantine fault tolerance, and it's a PFT protocol that has a communication complexity of a quadratic communication complexity, and one of the bottlenecks is actually the voting. We've also seen other bottlenecks like the large block, and I think the project called Mir tackled that one, and in this case here we look at the voting phase basically. And optimistic protocols, they now have a very nice assumption. They say, okay, if all of the participants actually are honest, then we can do it much faster, right? We only have this fault tolerance, Byzantine fault tolerance, because participants can act maliciously or even faulty. And if something like this malicious or faulty behavior is detected in an optimistic protocol, it falls back into pessimistic mode, preferring safety over performance in this case. And that means in the worst case, the performance is the same as for regular protocols, but in the optimistic case, as long as everyone behaves honestly, can be much faster. And that was the idea. And some kind of these optimistic protocols already exist in the classical sense of consensus protocols, basically. And we had to look at these and were inspired and tried to build something like this for blockchains. So a quick overview over this part of the talk. I'll give you, or I already gave you some motivation actually. I'll also have a look again at consensus, other kind of consensus protocols. Mainly Tendermint, Bitcoin, and Algorand, and I think you've also heard of some of them before during this school. So I hope that this is some kind of recap basically. And after that, I'll talk about our own protocol, the Albatross protocol. I'll also discuss with you the security and the threat model, and conclude with some future work that we're working on. And yeah, exactly. And during this part number 2, the Albatross protocol, I will focus mainly on the intuition on how the protocol works, but we also have a paper out there on preprint that goes into all the nitty-gritty details. Basically. So let's talk about PBFT again. In PBFT, classical consensus protocol, we have a closed set of n number of nodes. In this case, we have 3 nodes. And in PBFT we have a leader. One leader, and all of the other nodes here are called replicas. And now, of course, the leader can be malicious or faulty, and in that case we can change the leader. That's the main idea. And now, to basically accept a new state in PBFT, there are 2 rounds of voting. The communication complexity is quadratic, and you can see that in a moment. So here we have some kind of block or some state, and it has 3 phases, PBFT. The first one is called pre-prepare, and in that phase the leader sends out his proposal of the state basically to all of the other replicas. In the next phase, the prepare phase, this is one of the 2 voting rounds, and all of the different participants in the protocol, they have to vote on this proposal and send it to all of the other nodes. And here comes the quadratic communication complexity in. So every of these nodes then collects these votes and needs 2/3 of all participants' votes to proceed. And if the 2/3 of the votes are collected, we go to the 3rd phase, the commit phase, which is another round of voting. So again, quadratic communication complexity here, and all the votes are collected, and there's again the 2/3 bound to proceed. And if you have 2/3 of votes from the prepare and from the commit phase, the state is being accepted. And others can also verify it by looking at the votes, basically. And this kind of protocol provides optimal resistance against Byzantine nodes. That has been proven, and the bound basically is this n-1 divided by 3. So you can have, you can't have basically resistance to more than 1/3 of malicious actors, at least under certain assumptions like being a deterministic protocol. Yeah. Okay, and now you might wonder, 1/3 of malicious actors, but proof-of-work-based protocols, aren't they resistant against like 50% of malicious actors? And yes, depends on what kinds of attacks you consider, but you've also heard of selfish mining. Selfish mining can actually reduce this bound to 25% for proof of work. Okay, so what happens now in PBFT if one of the nodes behaves maliciously or fails? Let's say it's a leader here, the one that should actually propose the next state. In that case, all of the other nodes, they can vote basically during a so-called view change and say, yeah, we didn't receive anything from the leader, so we need to change the leader. And if 2/3 of the votes of this view change are collected, just round robin, the next of the participants will be the leader, and that one can then propose the next block, and the 2 rounds of voting, prepare and commit, can continue. Okay, that's how PBFT works. Now, if you want to transfer that to a blockchain setting, and you don't want to have a permission blockchain, then you have to handle basically not having a closed set of n nodes, but an open network. How can you do that? And Tendermint was one of the first protocols that actually went this route. It is very similar to PBFT, but the main differences are that the leader changes every block. So even if you don't view change, after one of the states has been committed, basically, the leader changes. In PBFT, the leader stays the leader until it's faulty, basically. And the second main difference is that the set of validators is determined externally. So, because validators in this case are the closed set of n nodes that actually participate in the PBFT protocol. Because PBFT is only designed to work with all the participants known up front. So if you want to have an open network, you have to select parts of this network to participate in the PBFT. And here it's determined externally and then pushed into the consensus whenever it changes, basically. And so the persons that vote on it can then vote whether they want to change actually the set of validators. Okay, another kind of blockchain protocol is Bitcoin. It also uses something like BDLT. Actually, it's an open network compared to Tendermint. Tendermint still has this closed set and being determined basically by someone externally. And in Bitcoin, we have an open network using 2 separate chains. We have a slow proof-of-work chain, and that one is used for the leader selection and also to select the validators. And with validators, I always mean basically the set of nodes that participate in the PBFT and the consensus voting and so on. And they call the slow proof-of-work chain basically the key chain, and it contains key blocks. So in this case here, you can see we have some key blocks, and the winner of the proof-of-work basically is the leader of the current round in the second chain, and the second chain is a fast PBFT chain for the transactions, and they use so-called microblocks. So that means starting from block number 1, where V1 is the block, the proof-of-work winner, V1 is basically the leader on the lower chain, and V1 is able to produce blocks there as a leader in PBFT and add transactions, and then as soon as there's a new block on the proof-of-work chain, here where V2 is the proof-of-work winner, that one will be the next leader on the other chain, on the fast PBFT chain. And the other set of validators is then basically a sliding window over the proof-of-work winners up there. Okay. And they also managed to reduce the communication complexity by using a tree-based signature aggregation scheme instead of sending it around to everyone, basically. Okay, so let's talk about another protocol, Albatross. And Albatross also has an open network, and I also very quickly, if you attended the Lightning talks yesterday, I also talked about that. Here they use verifiable random functions to determine the next, basically, block producer, and they also use verifiable random functions to determine basically the people that are eligible to vote, and that basically corresponds to a dice roll, just weighted by stake. That's why it's a proof-of-stake protocol. But they don't use PBFT. They use something similar though. It's a Byzantine agreement protocol, and the committees, so the validators, are chosen instantaneously, also by this dice roll. And the very nice thing about it is that everyone can basically check privately whether he or she is part of the committee, and then immediately vote together with the proof that he or she was part of the committee. And that provides this resistance against adaptive adversaries, because if someone wants to DOS basically the committee, he or the attacker would have to know beforehand that a person is part of the committee. But since everyone can only check it privately, they don't know it beforehand. Okay, and so these were the 3 protocols basically that mainly inspired us with Albatross. And so let me talk about Albatross. In Albatross we also have 2 types of blocks, but we have only a single chain. The 2 types of blocks that we have are macro blocks. These are PBFT based. They finalize the so-called epochs and determine the next validators. And macro blocks, they don't have voting, they have deterministic reducers and contain transactions. So in the picture here, you see one of the macro blocks, and it is followed by a number of micro blocks, and then again followed by a macro block. And so starting from the first micro block until the macro block, this is an epoch, and you can see that the macro blocks basically at the end of an epoch, they finish that epoch, and they change the set of validators that will then create the next macro blocks and vote on the next macro block, which in turn will change the validators. But we'll have a look at that right now again in more detail. So we need some randomness right here, and we do that very similar to how Algorand does it. So each of the blocks actually contains some randomness, and the randomness of the next block is created by a verifiable random function. So randomness is then used to determine basically who's the next block producer, and you can basically think of it like this. So in the microblock here, from the previous epoch, we have a list of validators, and then for the microblock number 1, you have to take the randomness from the previous block, hash it together with the view number, and what the view number is we'll see in a second as well. But basically the random seed determines who is the next person to produce block. And that means that only when publishing, for example, block number 2, we can know who's the block producer of block number 3, and only when this one is published we can know who's the block producer of the next block. Okay. So now we talk about the optimistic case. In the optimistic case, we assume that everyone's honest. So this is a very fast way. And so this is exactly what I said. Given the randomness R0 here, in the macroblock, we can determine the block producer for the block number 1. The chosen validator then creates and signs this microblock, and it's really like that. There's a one deterministic block producer for block number 1 that just takes some transactions, puts them into the block, signs this block, sends it out to the network. So very fast. And this process just continues until m microblocks, and this is a parameter of the blockchain, have been produced. And then given the randomness in the last microblock of the epoch, we can determine the block proposer, so the leader of the BDLT, for the next macroblock. That one creates the macroblock, and then based on the randomness in the macroblock, the next list of validators is chosen, basically from people who staked, so they had to lock up some funds, and from there we can randomly choose the next set of validators. Then this block proposal from the block proposer is signed just for integrity reasons and sent to the other active validators. And these active validators, they finalize that using the normal PBFT voting, just as we have seen it. So this is the only time that PBFT is actually needed with all of these voting phases. And once enough signatures are collected, this block is finalized and can be appended to the blockchain. Okay, so let's talk about the pessimistic case. In the optimistic case, we have, as you can see here, a lot of these microblocks that can be produced very fast, deterministically, and then at the end we have this voting, this PBFT, which is a bit more heavyweight, basically. In the pessimistic case, let's see what can go wrong, actually. So a validator can produce multiple blocks, for example. So let's say here in block number 3, a validator just produces 2 different blocks. So the same validator produces 4, basically. What can go wrong? A validator could not produce a block at all, either intentionally or it goes offline. So there's just some block missing here, and the validator then was supposed to deterministically produce that block, just didn't do anything. Or a validator can produce invalid blocks. These are basically the main cases that can go wrong in this, from the optimistic way to the pessimistic case. So let's have a look at these in a bit more detail. Forks. Usually a problem that you encounter with a lot of proof-of-stake protocols is the so-called nothing at stake problem. And that means, the person that is the next block producer can just produce 2 different blocks. For example, for double spend, one contains this transaction that basically spends the coins to the merchant, and the other block doesn't contain that transaction. Yeah? And you want to prevent that, and the usual way to do that is to slash validators. So in our case, when someone else encounters 2 different blocks at the same block height, you can build a proof. Because you can just, you have the signatures for the blocks, so you know it's from the same person. You have the block headers, and you can include that in the proof. And the validator that produced these 2 blocks will then be slashed. That means part of the stake is taken away and given to the others as a reward. So they also have an incentive to basically create these proofs and include them into the blockchain and punish the misbehaving validator. Exactly. So let me go back to the animation. So in this case here, we have two validators. They both have a stake, and here this validator on the right hand side created a proof for the misbehavior. So the two blocks basically that shouldn't be there because it's a fork, and that means that part of the stake of this validator on the left hand side will be slashed and given to the other validators. In this case, we only have two validators, and so it goes to the right hand side. Exactly. So, what about delays? That means a block is not produced at all. So, let's suppose we have the blockchain until here, basically, and then the next block is being produced, and that went quite fast. But for the next block, it just I have to look at the animations here. Okay, it just took too much time and the block timed out. So what we do in Albatross is we have basically, in this case, everyone has a counter, and from seeing the last block, checks the time until the next block arrives, and whenever basically this timeout occurs, people start a view change mode, and that happens just like in the BDLT case. And if two-thirds of the validators basically vote for a view change, the view number is increased, and the view number is just like the block number, a number in the header, and that results in a new slot owner. So that means deterministically, in this case, having a proof that two-thirds voted for changing it, we can still deterministically choose another person to produce the block instead. Exactly. And then everything can just continue as normally. So what happens when someone creates invalid blocks? In this case, these invalid blocks are simply ignored. And also any other blocks and the same block number from this block producer will be ignored for DOS prevention. Otherwise, you could just create multiple of these invalid blocks. And this will also then lead to a view change, because we won't accept any block, even if it was valid from this specific block producer, because it sent us one invalid block at this point in time, basically. And that will trigger view change mode, and after the view change mode, someone else will continue. And so basically, Albatross counters most of the Byzantine behaviors by view changes, and that means when someone behaves maliciously, we have to use the view changes, and that basically is the pessimistic mode, and in the pessimistic mode we have to change the validator, and exactly, so this is a way to basically switch from the optimistic mode to the pessimistic mode. Okay, so that was the part about the protocol, and now I'm talking a bit about the security assumption and the threat model that we have here. Albatross closely follows the model of BDLT, so we have a network that may fail to deliver messages, delay them, duplicate them, deliver them out of order, and we assume safety. For proving safety of the protocol, we assume a fully asynchronous network, but for liveness, we need some form of partial or weak synchrony. And we also, just like BDLT, we assume we can show that in a static case, that means the adversary is able to corrupt nodes at the beginning of the protocol, but not during the run. Then we are also resistant up to n-1 divided by 3 malicious validators, which is the optimal case for BDLT-like protocols. But if we assume that the adversary is adaptive, so that means that it can actually, during the run of the protocol, change which nodes to corrupt. In that case, the adversary can harm liveness, actually having less than n-1 divided by 3. And he does that by preventing the current slot owner from producing blocks, just tossing the current slot owner, basically. But our assumption basically here to counter that is that the adversary has just too little time to corrupt the next node, because between the microblocks, publishing the microblock and producing the next one, it's too little time to corrupt the next node, basically. And as long as that holds that the time to corrupt a node is larger than the time to produce a block, we are also secure against adaptive adversaries here. Okay, and now this bound that I told you about, this about 1/3 of the malicious validators, that is of course with regards to the number of validators. But since we have a proof of stake model here, we would actually would like to have this bound with respect to the stake instead of respect to the validators. But if we assume that we have n validators in total and the adversary is controlling a fraction p of the stake, we can express the probability of controlling at least x validators by the binomial distribution, and from there we can bound it, and we want basically this bound to be negligible. And if we set being negligible, for example, to something like 2 × 10 to the power of -5, but you can also insert some other numbers, then you get out some other guarantees basically, and we say we have at least 500 validators, that would translate roughly to controlling less than 1/3 of the validator list, being equivalent to controlling less than 1/4 of the total stake. So from there you can basically say that Albatross is secure under these assumptions. So as long as these assumptions that we have hold, our Albatross protocol can be secure. Okay, so a very quick pre-summary basically. We implemented that in a simulator, and this was just a fast and efficient way to evaluate the protocol parameters and the performance for us, and it's also open source. Basically, all of our stuff is open source. If you go to our GitHub, you can also find a browser-based blockchain and so on. And we also have a tested implementation, or we're currently working on it. It's already running without any optimizations, but yeah. And we want to have some implement some optimizations. One thing I talked about yesterday in the lightning talks is the single secret leader election that would give us resistance against adaptive adversaries. And the second thing is that we're currently implementing some form of light client, so we can prune all of the microblocks. And how does that work? So in Albatross, as we've seen, microblocks are responsible for storing most of the data. Actually, all of the transactions are contained in the microblocks. But if there are no transactions, we have a lot of blocks that are empty or just contain a small list of transactions. So a lot of data is actually not necessary. We could say, okay, we just require microblocks to be not empty, but that will just lead to validators creating fake transactions to build microblocks because that gives them rewards. So this won't work either. So what we decided for is we use the microblocks, which finalize each epoch. That means there can't be any forks after. So when you have a macroblock, there cannot be a fork before the macroblock afterwards. And we use that to summarize all epochs transactions in the macroblock just by basically having a accumulator, so a hash of all of the transactions. And that allows us to basically use the microblocks as a way for fast ordering and confirmation of transactions. But after having the macroblock of epoch, the microblocks are not really required anymore. We could throw them away and just synchronize the macroblocks basically. So let's finally summarize what Albatross is about. It's a novel and speculative consensus algorithm, or also optimistic. It's close to the maximum performance for a single chain algorithm, so that should hopefully improve the poor scalability issue. It offers finality at macroblock level, so not at every block, but at macroblock level. And the nothing at stake problem is basically countered by slashing, and a less decentralized network, which is often an issue with current proof of stake networks. We try to counter that by having an open network with frequently changing validators. The real world performance, we don't have results yet, the testnet implementation is currently what we're working on, and so hopefully we'll have very soon some updates on that one. And so I'd like to conclude my talk with a very small hackathon primer, because that's what will follow after the break. So we also try to focus on developers. As I said, we want to be easy to use and integrate. And we hope that JavaScript and WebAssembly actually allows developers to easily develop applications, web applications, or other applications that depend or use the blockchain. And so we have two kinds of APIs. The Nimiq Core API that basically handles all the blockchain internals, so you can create blocks, contracts, and so on, and you can use that from JavaScript in your web page. And the second one is Nimiq Hub and KeyGuard APIs. That is responsible for key management, signing of transactions, and so on and so forth. And Søren, a colleague of mine that's sitting down there, he will talk about that in the hackathon right after the break. Okay, so I thank you very much for listening, and I hope that you have some questions.
Okay, let's thank the speaker for the next part. We have time now for questions.
Thank you for your talk. I have a question about the first part of your speech, where you said that you are currently integrating some other cryptocurrency to pay in Nimiq, right? And my question is, how do you think to integrate other cryptocurrency? Relying on other exchanges, or have you some other idea?
Actually, that's maybe a good question for Søren, because he's working on that.
Right, hi. It's not a deep integration in the beginning. It's just currently we are working on supporting Bitcoin and Ethereum in the Nimiq checkout, so that the merchants only have to install one plugin, the Nimiq checkout plugin, to have the easy-to-use Nimiq cryptocurrency, but also have people buying with Bitcoin and Ethereum. But not integrated into the safe, not integrated in a browser wallet or something, just as support in the checkout, also via the external wallets.
But maybe as an addition, there was also a project called Image Wallet, and they basically tried to implement something very similar to our web experience with other currencies as well, but I'm not sure that they are actually continuing. So, but you might check it out.
Are there more questions? Why do you think I have one? So you showed a couple of slides before that you were doing some performance tests and you're still around.
Yeah.
Do you have some exclusive news about like some first numbers, how it would look like? Or?
So I think one of our guys did some first measurements regarding transactions per second, and without having any optimizations, it was already around like 1,000 transactions per second.
Looking forward to see that. More questions? Good. I have a second one.
Okay.
So at the beginning you showed this video about the user experience, how the users will look like when they use the Nimiq wallet. And if I didn't understand, or if I understood correctly, it seems like as soon as the transaction is signed, the shop might accept the transaction, or the shop is actually delivering the good.
Yeah.
And what will happen if the transaction is done spent or the user wants to spend it?
I mean, it's also the decision of the shop when it basically sends out the package, or if it's an online shop just selling online stuff, it can also wait until the transaction has enough confirmations. But for the user perspective, basically it shows, okay, the order has been received and transaction is out. So in the normal case, basically it should be the best user experience.
Hi, for your consensus protocol, I have one question, and that is for the microblocks. What happens if the leader selectively withholds parts of the microblock chain to some of the participants?
Withholds.
So not all of it, you know, like I'm an adversary and I selectively only send the whole chain to a subset and maybe just the last block before the next leader would be elected to some others. So people are missing some of the data because you would need the whole chain, right, to actually see if it's valid.
And he's withholding it to other validators, you mean? Or?
Yeah, but not all of them, just a subset.
Okay. So it depends on how many validators he withholds it to, because they will time out and will start a view change. So if he basically withholds it to more than 2/3, then they can start a view change and choose a different leader and will just continue from there on. And the chain selection rule basically says that always the chain with the highest view change number is the right one. So the defaulted chain basically would become invalid. But if it's less than 2/3, then the others.
So you might get into the situation that the next leader doesn't actually have the information it's required to build upon that, so it must kind of fork back and declare this chain invalid, right? Or
not forking back, but you could basically, by doing that, stop the other validator from being able to produce new microblocks, and that would later on then lead to a timeout again.
Well, I have some more questions, but I think we should take this offline because the protocol is probably complex.
Okay.
What are the next main milestones that you have in your development? Which are the next features that you are planning to release with Nimiq?
So we're currently working or implementing the Albatross protocol, and we also have some more changes that we want to do. Basically, currently we have this account stream model, and we want to switch to some hybrid between UTXO and account stream model. And this is something we're working on too. And after we have that, we will probably release that as a testnet. And after that, we're looking at privacy solutions. So we would really love to have some opt-in privacy at least in the chain, and that's something we're looking at too.
That was interesting, so I need to follow up. Why do you think that the hybrid between UTXO and account-based or address-based addressing makes sense? What is the advantage for that?
So the idea we had is, in the classical account stream model, you have the nonces, and I explained why we didn't like the nonces, we replaced them by the validity start window or validity start type, but this is also not really user-friendly because then you need to know the current height of the blockchain and stuff like that. And if you have a hybrid between the UTXO and account stream, you still have an easy way to prove balances, but you don't need basically nonces or validity start height. So you have to store more data, but in the end it's basically very similar as having the UTXO set and building a tree about that.
Thank you very much for your talk. Actually, during your talk, I just created an account for myself on the website.
Okay.
I found it very simple and easy, and that was nice. On the other hand, I was thinking regarding security, because everything is basically based on web browser authentication, and all the data is actually sent to the browser, to the user of the browser, instead of any server. So, have you considered any fraud detection protection algorithm here? Because I was thinking that might be kind of that's easy basically to spoof user authentication here and access to the keys.
So you mean basically someone creating a web page that looks very similar, or do you mean that basically hacking our server and delivering a different script, or?
I mean, if I somehow access to the keys by running some JS code, and or maybe by phishing, something like that, then I can easily basically have access to a user wallet. So I mean,
yeah. So for that, basically we fully rely on the browser security model. So as long as, because the keys are stored in this origin under keyguard.nimiq.com, scripts can only access that when they are the same origin. So either, of course, there could be some program running on the computer that basically accesses the web browser from the outside and steals the keys like that, but the same can happen if you run Electrum or even a Bitcoin client on your machine. So from within the browser, other scripts can only access it either if there's a browser bug, yeah, or if it's running in the same origin. But we are thinking about some basically fraud prevention mechanisms on the side that if someone would be able to hack a server and deliver a different JavaScript, this one might access the keys because it's running in the same origin. And for that we want to add some more protection layers, basically with code signing and intensive caching of the data of the scripts, so that it's not easy to replace the script, basically.
If not, let's thank the speaker again for the next talk.